Hi guys, welcome to JIK 224 E-Kuliah series. I'm Dr. Sumia Sabah and this is the 7th video covering chapter 2, which is diastereomers. In the previous video, we have looked at enantiomers. So there are two more types of compound that you have to know, which is diastereomers and mesocompound. So mesocompound I will cover in the next video. So what is diastereomers? Upon completion of this topic, you should be able to identify pairs of diastereomers and explain how they differ in their physical properties. Let's recap what we have learned from previous videos. Enantiomer. Enantiomer is the stereoisomers that are non-superimposable mirror images. They have opposite configuration at all chiral centers. Diastereomers, on the other hand, is that stereoisomers that are non-superimposable, non-mirror images. So, both enantiomer and diastereomers are non-superimposable. But enantiomer, it has mirror images, while diastereomers, it has non-mirror images. So, diastereomers have opposite configuration at some, but not at all chiral centers. So, this is the difference between enantiomer and diastereomers. In general, diastereomers fall into two categories. First is molecules with two or more chiral carbons. And second, geometric isomers such as cis and trans, since they are not mirror images. So for example here, we have cis but2n and trans but2n. So these are actually a pairs of diastereomers. It has a similar configuration on one side. Okay, if you see here and at your left here, we have C, CH3 and H. It has a similar configuration here with the trans isomer C, CH3 and H. But on your right, we have a different configuration where the methyl group will be at the top, while at the trans isomer we have the methyl group at the bottom. So this is what we said, it has opposite configuration at some position but not at all position. So this is the main difference. Cis-trans isomers on ring are diastereomers. We could also have a pairs of enantiomers. For example, trans 1,2-dimethyl cyclopentane. Here, this is the trans isomer and this is the cis isomers. So the trans isomer, we have a pairs of enantiomer. We have a non-superimposable mirror image to each other of both of the trans isomer. Remember, trans isomer is when we have the functional group of interest in opposite direction. So here we have one methyl group facing up and one methyl group facing down. While on this second enantiomer, we have one of the methyl group here bottom and one in the top. So there are pairs of enantiomer. But for cis isomers, we have the methyl groups, both of the methyl group facing downwards. So they are achiral. Why? Because they have an internal plane of symmetry. So they are achiral, and actually this both of compound 1 and 2 here are diastereomers to compound C here. So this is what we call diastereomers, because we could have one part of the cis isomers here similar to one part of the trans isomers, and one will be different configuration. Molecules with more than one chiral centers have pairs of enantiomer and pairs of diastereomers. So for example here, we have 4 compound. Compound A and B are actually a pair of enantiomer, while compound C and D are a pair of enantiomer. So we have here 2 pairs of enantiomer. You can see here that compound A and B, they have non-superimposable mirror image, and compound C and D here is also non-superimposable mirror image. So from these 4 compounds, we could actually find pairs of diastereomers. So for this compound, A and B are diastereomers of C and D. So A and C is a pair of diastromers and B and D is a pair of diastromers. Here, you can see here between A and C, the compound on your right is similar to the configuration in C, but the configuration at the left here is not the same as in C. So this is why there are a pairs of diastromers. The same goes to a compound B and D here. It has similar configuration on your left, okay, here, but they have different configuration on your right. So you can see here the Br is facing backward, further away from us, while in B the bromine group is facing towards us. So this is the difference between enantiomer and diastromers. Okay, let's look at this example. Can you identify a pair of diastromers from this compound? From here, A and B is actually a pair of diastromers. If you are wondering, this is actually a Fischl projection. So in the later videos, you will learn how to draw a Fischl projection. Fischl projection is actually a flat representative of the 3D molecules. So from here, A and B, A have a similar configuration with B at the carbon number 2. So this is carbon 1, carbon number 2. So both of these is a chiral center. So at carbon number 2, we have a similar configuration between A and B, and a different configuration at carbon number 1 of A and B. So there are a pairs of diastromers. We could also have a pairs of diastromers at compound C and D. They have a similar configuration at carbon number 2 and different configuration at carbon number 1. For the second example, please draw all possible stereoisomers for the following molecules, then pair up between enantiomers and diastromers. So here we have a cyclopentane with hydroxy group and methyl group here. So this is supposed to be a methyl group. So remember, when I did not put any carbon here, this means the dot here means that there is a methyl group. To determine the number of possible stereoisomers is that for a molecule with n stereogenic centers, so in this case we have 2 stereogenic centers at this carbon and also at this carbon. So this is carbon 1 and this is carbon 2. So the maximum number of stereoisomers is 2 to the power n. So in this case we have 2 stereogenic centers. So 2 to the power of 2 is equal to 4 stereoisomers. So you have to draw all 4 stereoisomers of this compound. So what you can do here, so there is 4 possible stereoisomers, is that you draw all the cis isomers and also the trans isomer, and then you can draw its mirror image. So in this first, we have a cis isomers, and this dark line means that the functional group is pointing towards us. So draw the mirror image of this. So first we assign this as compound A, and then we draw the mirror image, and this will be compound B. And then next you draw the trans isomer. The trans isomer is when you have one functional group facing towards you and another functional group is facing at the back. So this hydroxy group is facing towards you and this methyl group is at the back. So draw the mirror image of this and you will get compound D. So A and B are enantiomer and C and D are enantiomer to each other. But A is the diastromers of C and D, so A is a pair of diastromers to C and also D, while B is also a diastromers to C and D. Here, we see that A and B are non-superimposable mirror image. The same goes with compound C and D. But for A here, it has similar configuration with one part of its functional group have similar configuration with compound C and also D. while for B, it has also a similar configuration with compound C and D. The difference between the properties of diastromers. Since enantiomers have identical physical properties, they are difficult to be separated. Diastromers, on the other hand, have different physical properties. They have different melting point, different boiling point, different density, refractive index, and solubility. So, for example, here we have this compound is carboxylic acid. They are diastromers to each other, and therefore their melting point actually will be also different. One compound has 158 degree, while the other compound would have a melting point of 256 degree. So they can be easily separated by common physical technique such as distillation, recrystallization, and also chromatography. As a summary, diastromers are diastromers that are non-superimposable mirror images and have opposite configuration at some chirality centers. Most diastromers are either geometric isomers or compounds containing two or more chirality centers. And diastromers have different physical properties, and they can be separated easily by common physical techniques. This is the reference. And if you have any question, you can email me at my email address. And thank you for listening.